maximum amount positive or negative 30 non-decreasing order, and maximum arbitrary number. Numbers positive, number is positive, then maximum. Okay, so just counting. Find the maximum count of positive and negative. Count them. So first we count negative and positive. If the x is 0, what is it? 0 is near, alright, so x is greater than 0. That's the idea. Okay. Maximum score after different k operations. Starting score 0 operation, we choose the index, increasing the score, and replace it. Alright. K operations. What is a K? It was simulated. Okay, we can simulate it. Find the maximum K element. Idea is heap cell. Okay, so priority queue of list, we choose the max heap. Okay. Search, and X is pick its hub. Push the cell. X. Okay. Cool. Say the problem 3. You given your index word 1, word 2, and move consist queues to index. Usually such that swapping. You can choose to get the numbers of distinct characters in an equal with exactly one move. Okay, distinct. Score. Use one move to make distinct number is equal. Sorry, so this is false because we cannot choose it, right? Because there are 2 and this has 3. If we swap it, okay. So consider this kind of information. First we calculate the distinct. We only can swap 1. That means if this is single, you're decreasing. So it's actually we can decrease. Okay, this is equal. It's written true. So what is can use a map to do that, right? Some cases once if the same true and only one move is that if not the same and A to B, if A is greater, else if A to B is that we can choose one to swap this. Right, so second case is word 1, map 1, word 2, map 2, and 1. If the word is equal to map 2 size, return true. This case 1. Map 1 size is greater than map 2 size. Swap. And swap word 1, word 2. So that makes sure map 1 to map 2. So, okay, we check this. So if this is 1. Okay, and should be 1. So for the integer in the array, in the map 1, want to move into, we can decrease, right? So if this is 1, identify that. If map 2, we can count the K and the B, count the B. Also, we have the character that is also C is not equal to K. If map 1, map 2, count C and map 1, count C, they both have this, we're greater than true. That's the idea. Let's care for the case. Yeah. Alright, so the first case is that if they are equal size, equal distinct number, and the distinct is greater than 2, and if this is I find one move, we move this character, try move this character if this exists, so we can move it. After we move it, we're moving this. Okay. Oh wait, okay, so C, you know C, is that if we move it, to B, and map C should be greater than 1, because if it's greater than 1, that is not false. Oh my goodness. Map 2 should greater than 1. Alright. Alright, so B. Okay, this is true. Huh? Wait, why? 16 characters is roughly 1 move. Oh. Exactly 1 move. Exactly 1 move. So if they are equal, they can swap this. And falls true. This kind of information is that index we swap this. Okay, so it's not equal to 1. Sync. In this example, saying that this thing is the sense, so many cases. If this is 1, also we have a character is 1. Should be 1. This equals doesn't matter. We're saying that map 2 is 1. We don't care this. We only care is if we have both 1. First case is okay. We can swap. This is the first case, we can swap the same characters, and if we cannot swap the same characters, let's say in this case, we can decrease, right? So we decrease then. We only need to do is 1, and if this is 1, also 1. Also the we don't care this, but let's say we cannot increase. Okay, I want to swap. So I want to swap the K. I want to swap K, and I don't want to increase this. So this kind of information is saying that it's map 1, map 2 both have this. Both have this, and if okay, wow, it's a little interesting, because there are less ones. we need to choose is that they don't increase, so it's a map 1 account. Not counted. Map 2 counted. Also what? Because they are let's try. Not counted. Let's say map 2 count. Let's see. Right, so if 0 to erase C, map 2K plus size return true. Otherwise decreasing. Actually, you can simplify to what? Okay, I hate this. Let's see. We try to swap this. So if map 1 count C, can swap 0. I think we can just use this. It's general and yeah, it's general. C0 and if we count this, so we want to swap C0 to this, so we say okay, map 1 C0 And we will get it that it's we try to move it to move C, move C, move C. C0, map 2. This one, and also we are decreasing our C, increasing then, and cover it. And also we are moving C to map 1 plus. We also are moving C to this, right? So we're moving this, decreasing this, this, and we are decreasing this. This map 2, this map 1 is they are decreasing this. Map 1 is C. If they are increasing this information and decrease erases. Alright, so shit. False, true, false. ABB is false. This is true. Alright, I hate this. Okay, I don't know. So stupid. A lot of cases you need to consider that. Yeah, so shit. Okay. Wow. It's a hard problem, right? Nobody solved it. Alright, so what's problem statements? A little long. Workers, what it means? 2D every time is the size of case. Left to right, pick up, right to pick new. Want to move the inbox from the old warehouse to new one, you given 2 integers. And the erase time, the warehouse are separated by a river and connected by a bridge. The house is kind of information. Alright, so what is okay? So keywords as left side bridge to move the box. We have box and key workers, and also we have key workers left to right, and pick new. What is? And cross from left bank to right bank, we will have less minutes. Pick a box to or warehouse, return the bridge. Return bridge? What? Return bridge difference. We could pick on the part simultaneously. We can pick simultaneously. Cross a bridge from right bank to left bank. put a box new warehouse, return the put news. New warehouse. Okay. And on this reason page. Okay. So that means that for going to our warehouse and we pick a box to this and we go to okay. So the worker is less efficient than the worker J. This condition, the left to right is greater. Also, is greater and equal, and this is greater. Right. So small index. Okay. And the following rule regulates the movement. If the worker has reached the bridge while another worker is crossing the bridge, X will wait aside the bridge. If the bridge is free, the worker waiting on the right side gets cross the side more than one worker waiting on the right side. Lowest efficiency crosser first. Now it's free, no worker waiting on the right side. This one bus remain over the left side will get cross the bridge. More than one waiting on the left side at once. Wow. Instant times the last worker reach the left end after having put oh wow. Oh, some kind of shit problem. It's alright. I know why so. Okay, so waste a lot of time, I think. Right, so think. Alright, so from 0 to 1, 0 to 1. What? 0 to 1. Okay. Oh, this 4. Worker 2 has the less efficiency. And box is in the old warehouse. So in the worker 2 goes a bridge from left to right. Need 1 minute here. And we pick a old warehouse. In 1 minute, pick up 4 minutes. From right to left. We need 4 minutes. And what is the last index? We don't need to put news. Why they need to put news? Put the box plus left side, so news. Oh, so 7 minutes. 6, 7. 6x instance time the last will reach that point. So create a new warehouse. How do we do this? Wow, another case more, right? And just simulate it. I think I can do is that find the time that our workers back to left. What is idea? Right, so the bridge is free. This row is that bridge is free and worker waiting on the right side, and at least one remain at the warehouse. The worker on the left side will get close to the bridge if there is more than one. No, there's more than one. It's waiting. Okay, so they cross the river. At first, they are waiting the right side of the workers across the bridge, and after no waiting on the right side, and so backward first, and right side go first. Now the left side. Okay, so what is idea? Thing is simulated, but it's kind of shit. Given this example, you are the best of this because they are remaining one, and they don't right side doesn't have any kind of information, right? They can pick us simultaneously, right? So the different workers and pick up their box simultaneously. Actually, that means just that we only carry a bridge. We don't carry bridge. We only carry left to right. I mean, we don't carry this. If we don't, we have to left to right. We have to left to right. This and but a worker reach well crossing weight. That's free waiting at right side gate. So but it's waiting, right? So if it's not waiting, left side available, go first. Well, what? Let's go to time. Well, because the time is smaller. The time is more, so we can do is It's hard, right? And I need to think. Let's see this example. So the list two workers, and also we have let's see efficiency. Let's see efficiency. Okay. So I think it's each worker we equals values. And we may use a heap. Use max heap. We may use max heap. In this information and and some kind of shit. Bridge is free or not? Bridge is free. How do we know bridge is free? So we know the time. Now bridge is free, and we are going to do that. Okay, so we need the time. We need a time state. Need a time state. Time state. We can know the bridge is free or not. And they are busy. So it's a heap problem. So let's just see another example to make sure my approach is that we may have available and also we have a busy waiting. Not a busy waiting. It's a they are pick up or they are put some kind of queue. When we are arriving, we will add so set count. Okay, so let's see. And let's say this worker one is good, and they need they are greater. So from the cross to right bank, and worker one pickup needs 10. And now no more waiting, so worker 0 reach from left to right, and then I pick up. So I decide here. When we are moving this is available, and we add into the busy waiting. What is the left? So worker 1, when we are crossing length, and we need to pick up. So it's the left time. It's the current time must add the left to right time, and the current time will always be the live times for efficiency. More efficiency need time step and min heap for live warehouse. Okay, and what kind of so and workers K. Okay, this is K. So all the workers and overlaps available. So I need available RT. We need the index of this. This max heap. This is the left OK, right OK, left OK. Size is smaller than K. We are doing. Let's see the case. We also have min heap is left time and live. Okay, got here. Yeah, this right there. Also, we need the answers time step. Put name. Okay. Alright, I need to okay I and level case first is in the queue. So whether we can push into push this. And left OK will push efficiency of this. So it's time I 0 at time I 2 the I. Okay, so it's left OK. Alright, so okay, so we can choose this after if OK is not equal to OK. So this time we're going to do is that in this time that means the bridge is free. Bridge is free. And let's say the bridge is free, level OK, size. And left will go into the left. So time step will add, let's say current auto. We don't need this efficiency. We only need to carry the index of this left OK top. Time step will add left to right, so it's time I 0. So put it right, and the right lift will push the lift times the time step at the time I 1, because they need this time, this. And also we need its I. It's a right lift. And they are now OK, right? So let's say first thing is the left to right. If they are available, if they are free, and the worker is waiting on it, because going on word 1. So box open, word open. So first, if box is free, the worker waiting on the right side, they get close. Okay, so first is the right side. The right side, if they are free, the scenario of this two scenario we need to consider. Consider this is the scenario. Okay. If the box free rating on west side get closer bridge. First scenario. If there's no worker waiting on right side, remain in the warehouse. So this is two scenario. Yeah, so let's do scenario. And let's do scenario 1. Right side. So if free, waiting on right side. So left right OK. Size. What should do? If okay, if right OK size means they are the times they will add. Right OK. Right OK the pop. Times they will add. It's close to river. And also we need to do is that, well, write the time size and write the top, the first is it's smaller than the timestamp. Let's say right, okay, push we still need this. And if we still need this time at 2. Okay. The smaller and time state. If they are good, do left. Okay, so yeah, I think it's just simulate problem. So it's not that hard, I think. Maybe 50%. So I think it's sure. And actually activity are okay. And time is going to be right to left, so we'll add this time I2 onto left, right, and the left lift will push time step as 3. Oh, maybe we don't need this because we are index is recording our product queue, so we don't need this. And yeah, so left lift. So good. Do left size is that this should be do first. Left lift store. Then double OK will push it. Now I think it's let's do that. So continue. So what it means? It means if they don't reach it, they don't reach it right, and so no valuable first is a free, and they don't have waiting. And now it's a freeze, and the workers is on the left side. That means that if the both are failing, time step at 1 because it's not sure. And after they are picking it right, they are doing it picking it right. left OK, the right lift. Right lift, left OK, left lift, left OK. So while they are printing news, it's 3. What is 3? So good news. What is left, right? Left time, it's they go back to this. They actually so left, turn left and lift. And push it. Okay, Shingets. Shit. Alright, so bridge is free, right? So bridge is free. Or that side. Cool. So it's 0 and 2. Which one? It's time. Right, okay. This is the same because we need efficiency. We need the efficiency. This is efficiency, and we need this. This is the time and I. Efficiency and I maximum, then the time and I pair. So first is that what kind of information break. She also says, okay, let's see this. She usually have okay. Oh, they don't have okay? That's weird. So first, do left right side. The left is more than time step, so we can lift. And I pushing the OK. So if we have OK, we go back to the left side of this. And now the lift, it's increasing. Waiting, this, waiting. Why is this fail? Not sure. That's 2. Okay, so that's 2. 51. So first is that left to right in this time. Yeah, and so right to left in this time state. Let's see the example one. Cool. So from left to right is 0. So they are going to be equal. Left to right is 1. Left to right is so left to right is 1, and left to right is 2. Wait, what? Left to right is 2. It's wrong. Left to right is 1, and from 1 to 2. 1 to 2. Because they are peaking, but pick up box from old. Box 1 left to right is 1. So it should pick up close, otherwise closing by the side of this. This is pretty easy. Again, there's no workers waiting on the right side. Why they are worker 2's peak. So the peak is with the peak. Simultaneously. I don't understand is that it's this is never okay. That's not okay because they are 1, right? They are 1. The leaf is 2 because they need to pick up is the right leaf. The pickup is 2. So 2. Pickup is 2. Why we can close that? This is not free, I think. Wait, I don't understand. Because they are pick out a box. Two, put 1 to 2, they can pick out a box. Also 1 to 2, they can. Yeah, I think the 1 to 2. left to right is 2, and let's say the index of this. Yeah, I think this should be simultaneously. So in this first example, let's see that the 1 to 2 they also have a read because they are picking down, but they can move it at the same time, right? So this index is 2, and left to right, let's go into this here, and now after right to left, 6. So 6. After 6, the 1, 2. Oh, sorry, it's not 2 plus 4. It's speak up. So speak up. It's 2. Cruising, so it's 4. Cruising, so it's 4. Cruising, so it's 4. Yeah. Yeah, I think it's the live time. Live time. Yeah, 2 to 6 cannot do anything because they are parsing, so it's 6. After 6, oh wait. Oh wait a moment. So to right it and should decrease. So they cannot do anything. So if n is greater, n should be greater than 0, and yeah, so that's not decreasing then. I'm not sure, but let's say I consider this kind of information. They only can move with 1, 7, 6, 7. Yeah, saying it's 51. Oh, wait, it's 7. Why? Say, let's say this left to right is 1 to 2. It's left to right. No, it's 2. And now because we cannot going to do this, right? So after they are leaving, they don't have leaving, and they are not okay. 6, 6, 6. 2 to 6, they are pigs. And 6 to 7, they are a new warehouse. Right to left. From 6 to 7. Oh, so they are picking. Times 3 is 1. Wait, what? I don't understand it. I don't understand it. We go back to 2. The left lift is 7. Step 6. Is this left to right? Oh, yes. Good. Simulate. Oh, wow. Do it right side first. Apply the time step. Okay, let's finish this. Context. Well, I think just need to careful. We do the right side first, and also in the checklist, we cannot send in error if we have left OK because we cannot pick out anything. So yeah, we only can put is n is greater than 0. Oh wow, this should be really hard, and actually it's not hard, but it's the careful condition. Yeah, so yeah, that's it. All right. Waste some time, but actually, it's not hard, but the problem statement is very long, and you need to consider it. But I think this can be improved because why this can improve because that's why I use plus because the time is very small, so you can think about the time. Time step maximum is quite small, so we can just simple add. Otherwise, we can do is that we can check that what is the smallest we fast forward to force forward to this. Yeah, but yeah, seeing it's alright. Seeing it's done. But this kind of information is seeing just weird. 7 layer down, 7 layer down. I break it at 8. Can I restart in this? Because the right is going to back to the left. We can break it. You can break it. Yeah, there I go back. Yeah, so okay, that's problem 4. Okay, let's see the problem 4. I think the problem is that it's very, very long. You have some workers and you have K workers and you want to move in boxes. And each worker, we have this information from left to right and pick up from right to left and put new. And the information of these 4 values that occurs from left rank from left to right. We need this minutes, and we put the box from old to rich. We need pick up minutes, and you need to careful that different workers can pick out a box simultaneously. It means that if the bridge is free, they can go through here. If this is not down, we can go through again. So this is example 2. So yeah, that's the idea. And I see this conditions make the problem simpler because the less efficiency is the maximum left to right minutes and the maximum index of this. So that makes problem easier. And the following rule you need to consider. This is very, very important hint of this problem. Because if a bridge is free, they do the right side first with the lowest efficiency. If they don't have a right side waiting, that means that we can from left to right. From left to right is important. Have also important conditions that the box still have a box that we can move a worker. Because if we don't have a box, we cannot move the workers. You can see the example 1. Because from and the problem is want to return the last worker reach that bank. And yeah, you see this problem is you can you may have idea, but it's hard to implement. But now this simulate problem is I don't know, but just need to care for a lot of edge case. So yeah. Alright, so idea 1. See example 1. You may more understand the problem. They have 1 box, 3 workers, and each worker have this. And from the 0 time, we go cross the bridge because bridge is free. So left to right, we will choose this because this is the maximum. This is the less efficiency. And in 1 to 2, 1 to 2 is because we pick out the box, but if the n is 2, we can simultaneously from left 1 to 2 and use worker 1. Yeah, but since there are only 1 box, so we just pick up this. So we pick up. What is pick up? Pick up needs 1 time. And after we pick up, let's just go back. And go back, we just can already return it. We don't need to care to put new time. We just need to care that, okay, so if they don't have a box and all players are in the left side, we just already return it. So the idea is what? Idea is that we can use a max heap. max heap to first record list, second record list. And we also need to use its main heap for leave time. So that means the max heap of left OK, right OK. List is available workers, and they need to leave. So first thing, we just initialize they all have available in the left side. So pushing the heap, and these two scenario. First is a free, we're working on right side, so we do the right side first. And the condition is that if we have a box and the left side and right side is not equal to k, still can doing. But actually, I think okay, we can move this information to this to make problem easier. Not easier to make because this is no use, but doesn't matter. Actually, let's just do first right side first. If the right side have leave, we are if the leave is in a time, we can do what? We can pop into our available heap. And after we are choosing a variable heap, we need to choosing one waiting, right? The one worker waiting on the right side, we will choose to pushing to the left side here. So time step will add to right to left time, and also they are pushing the left heap. They need this time. After this time, they can leave. So continue this. If they don't have the right side workers, we just do the left side as almost the same. First, we pop out the available, another available. Not is this can be available because they are free. So they push in the left heap, and if they still have a box in the old house or warehouse, we can use the workers to send this. And this is important. This condition is important because first I made a wrong condition that getting to the infinity loop, and this is very weird. So this is important. Oh, this is hard to implement if this is the interview problem. There may be a dimension. So yeah, it's and if the neither this condition nor this condition, we just forward our time step until we can reach. So yeah, this can be improved, but it doesn't matter because the time is small. It make a problem a little simpler. And I think we can do. It's not equal to k. We can just return time step. I think. Yeah. Right. So we don't need this. We don't need this. Yeah. So I think this condition can be simplified to this. Yeah. That's a problem 4. Just I don't want to say the first. Let's see the problem 1 and problem 2. It's very simple. Very, very simple. So problem 1, just calculate the maximum, calculate the positive integer and the negative integer and return the maximum. And careful that the 0 is neither positive nor negative. So we just counting them. If they are positive, add a counter, negative, add a counter, return the maximum. This is part 1. Time complexity is linear and space complexity is just constant. Problem 2 is very simple. You have a score, and in one operation, we can choose this, increasing and replace it. And actually, because the k is small, so we can simulate it. And we can do until we are reaching it. So let's just use the max keep each time we choose the maximum. So let's just do simulate it, and this is a cell. Yeah, this is a problem too. Yeah, because the maximum score, you always choose the maximum value. You always choose the maximum value. You can actually you don't need to choose one, right? You always choose. This is greedy. You always choose the maximum. So the problem two is just like this. This is linear, and this is k log n. Yeah, k log n. About problem three, I think is just a shared problem, right? You will use exactly one move. Note this is important. Exactly one, and we want to make the frequency, the distinct character in these two words is the same. So actually, we can use a general approach. Is that we first calculate the frequency of this and enumerate this. So this is constant. This is constant. We just enumerate it. If they are counting, we want to swap. I want to swap to another characters and just decreasing length, increasing length. If they are counting, let's swap. Do swap. Do swap is we add a counter minus a counter. Map to map to is the word 2. So word 2, word 1 will add C, word 2 will decrease C, and also word 2 will add C0. So here just do if there are the frequencies the same, they return true, and recover it. That's just a problem. This is a general approach to make condition more simple. Yeah, actually, you can move to list 2 up. Yeah, and we can move to list 2 down. Actually, this is good. Yeah, this is good. Yeah, this is good. Yeah, that's problem 2. Problem 3. So yeah, that's all problem. Alright, so okay, thank you.